For this first lecture in our unit on atomic structure, we're going to talk about the nature of light. So we'll talk about the wavelength and frequency of light, the electromagnetic spectrum, and some of the behaviors of light waves. Light waves are characterized by a few key properties. So light is a form of electromagnetic radiation, which means it has oscillating electric and magnetic fields. You can characterize light waves in terms of their wavelength, frequency, and amplitude. Wavelength refers to the distance between peaks and has a unit of distance, something like meters, or millimeters, or nanometers. Frequency is the number of peaks that pass a given point per second, so it has a unit of inverse time, typically hertz, which is inverse seconds. Amplitude refers to the peak height. So to see these, let's look at these figures over here on the right. The wavelength is the distance from one peak maximum to the next. So this is the wavelength of this first one, this is the wavelength of the second one, and you can see that this second one has a shorter wavelength than the top wave. The frequency, as I said, is the number of peaks that pass a given point per second. And so if we think about that, this is how far a wave might travel in 1 second, we can see that there are 1, 2, 3 wavelengths that pass through here in 1 second for this top one. For the middle one with a shorter wavelength, it turns out you'd actually get 6 wavelengths passing per second. So whereas the first one has a frequency of only 3 hertz, the second one has a frequency of 6 hertz, and this third one has a frequency of 12 hertz because there are 12 complete wavelengths that can pass per unit of time. The amplitude, as we said, is measuring the height, and so that's the distance from the midpoint of the wave up to the peak. And we see that this upper wave right here has a larger amplitude than the lower wave right here. Now there's a key relationship between frequency and wavelength. In particular, they're inversely related via the speed of light. Qualitatively, you can see that here. In our longer wavelength example, we had a lower frequency. As we decrease the wavelength, moving down here, you'll notice that the frequency is increasing. Mathematically, the frequency nu is equal to the speed of light, c, divided by the wavelength, lambda. The speed of light is 2.998 times 10 to the 8th meters per second. The electromagnetic spectrum spans a wide range of wavelengths. The visible light that we're familiar with from our day-to-day lives is actually only a very small fraction of the full spectrum. So if you look down here, you'll see that the electromagnetic spectrum can actually span something like 15 orders of magnitude in terms of the wavelength. At very short wavelengths, we have things like gamma rays, X-rays, then getting to ultraviolet rays. Then we get to the visible region, but the visible region is just this very small window from 400 to 700 nanometers. Then we have infrared at slightly longer wavelengths, terahertz, microwave, and eventually the radio region of the electromagnetic spectrum. So as we move to the right along this, the wavelength is increasing and the frequency is decreasing. Or put another way, the frequency is increasing as we move to the left. Some examples of technologies and other features in which these different wavelengths occur are shown in these pictures here. So at the very long wavelength end, we have things like AM and FM radio. In the microwave region, we have things like cell phones, radar, Wi-Fi signals, microwave ovens. In the infrared region, we have things like your television remotes or night vision goggles. Visible light is, of course, what we're familiar with from our day-to-day lives. Ultraviolet light plays an important role in some chemical reactions. For example, it's used to cause the reactions that make the dental fillings your dentist uses cure and solidify. X-rays are, of course, used to penetrate your skin. And then you have even shorter rays and some cosmic things and PET scans and so on. A key feature here is the shorter the wavelength, the higher the frequency, and the higher the energy. Before we go any further, let's do a couple practice questions. First, a qualitative one about the wavelength and frequency of light. So which of the following light forms has the greatest energy content and the least? A, yellow light at 590 nanometers. B, an FM radio wave at 3 meters, C, a 266 nanometer ultraviolet laser, or D, a 940 nanometer infrared remote. Go ahead and pause the video and answer the questions, and then hit resume when you're ready to hear the solution. The answer here relies on remembering that the shorter wavelengths have higher frequencies and higher energy. So here we know that the radio waves are considerably longer at 3 meters than any of the other 3 in the nanometer range. And so we want to look for the shortest of these, and it's going to come from one of the 3 in the nanometer, and the shortest of those is the ultraviolet laser at 266 nanometers. The FM radio, being the longest wavelength, is going to have the lowest frequency and the lowest energy content, and so that's going to be the least energetic. Let's do another one, this time a quantitative one converting between wavelength and frequency. So a typical AM radio channel broadcasts at 1000 kilohertz. What's the wavelength associated with that band? So to do this, you're going to want to use the quantitative relationship we talked about before that relates the frequency to the wavelength via the speed of light. So go ahead and take a moment and try to work out this problem and resume the video when you're ready to hear the solution. So in order to solve this, we first want to convert the 1000 kilohertz frequency to a more basic unit of inverse seconds, remembering that hertz, 1 hertz is 1 inverse second. And so if we take 1000 kilohertz and we have 1000 hertz per kilohertz, we can do the unit conversion in order to obtain that this frequency corresponds to 1 times 10 to the 6th hertz, or 1 times 10 to the 6th inverse seconds. Once we know that, we can now take this equation and solve it for lambda, and we get this expression here. Now we can plug in the speed of light, plug in our frequency in inverse seconds. You'll notice we have inverse seconds in the numerator and in the denominator, so those are going to cancel, and we end up with 300 meters as our final answer. So the answer is B. It's a 300 meter wavelength band. The waves we've been talking about so far are traveling waves, similar to what you see on the ocean. But there's another special kind of wave that's worth mentioning. That's a standing wave. You've seen these, for example, if you've ever plucked the string on a guitar. A standing wave is a wave where the 2 endpoints are fixed. And it turns out when you have these standing waves, you can only have waves with integer or half integer numbers of wavelengths between the endpoints. So again, think of the guitar string here. If these are the 2 endpoints of my string and I start vibrating that guitar string, I can have half a wavelength here, or a full wavelength, or 1.5 wavelengths, or here 2 wavelengths, etc. But you can only have these complete or half integer numbers of wavelengths between the 2 endpoints. So this is an example of something we call quantization. We're going to see a lot more examples of that as this unit goes on. The other thing I want to point out about these standing waves are the nodes. A node is a point with 0 amplitude. So here's a node, here's a node, here's a node, here's a node, etc. So as this string vibrates, in these regions it's going to be moving up and down as the vibration goes on. But throughout that time, the node is going to remain 0. And it turns out, as the number of nodes increases, typically the energy content of the wave increases. And you can actually understand this from what we've talked about previously in terms of wavelength and frequency. So you'll notice that this one clearly has the longest wavelength because we only fit half a wave between the 2 endpoints. This second one has a shorter wavelength because we can now fit a complete wave between the endpoints, and this third one we can fit 1.5 waves between the endpoints, and so on. So as our wavelength is getting shorter, we're fitting more and more nodes in between the endpoints, and therefore the energy content is going to increase. Finally, let's talk about some of the wave-like behaviors of light. So light has a number of properties you've seen before. For example, reflection, where light bounces off a mirror or reflects off the surface of a lake. Refraction, where light bends when it enters a different medium, such as water or a prism. For example, you've probably noticed this when you stuck a straw in a glass of water and it looks like the straw is bending when it enters the water. Or diffraction, where light fans out after passing through a narrow opening. Here's an example of diffraction occurring with water waves. So we have waves coming in through this narrow opening, and then you can see the waves are starting to fan out from that opening. Light can do the same thing when it comes out of a narrow opening. Another interesting property of light waves is interference. So you've probably seen water waves interfering at the beach. For example, if you have two waves come together and the peaks of the two waves combine, you get a constructive interference where the wave doubles up in height. In contrast, if you have the peak of one wave hit the trough of another wave, the wave cancels somewhat. That's destructive interference. Well, similar things can happen with light. So a really great way to see this is through something called the two-slit experiment. And so the idea of this two-slit experiment is right here I have a light source that's emitting light. Maybe it's a flashlight or a light bulb or something like that. And back here I have a wall that I'm going to be observing the light on. In between the flashlight and the wall, I put a barrier with just little narrow slits in it. So first consider what would happen if we just had one of these slits open. So pretend I make a little hole here so my flashlight can shine through the hole and reach the back wall. If we did that, we would see a blob of light on this wall roughly centered around wherever the light is hitting directly past that hole. And of course it would fade away as you moved away from that central point. However, if I open two slits in this wall, as shown here, after the light passes through each hole, it's going to start diffracting, but the waves from the light passing from the upper hole are going to interfere with the waves coming through the lower hole. And you end up getting this interference pattern shown here, where you get these alternating regions of bright, dark, depending on where the waves are constructively interfering or where they're destructively interfering. If you want to see a nice example of this, here's a YouTube video you might check out that shows this two-slit experiment for light waves. So in conclusion, we've seen that the energy, wavelength, and frequency of light are all interrelated. The key idea is the higher the frequency, the shorter the wavelength, the higher the energy. We can also quantitatively relate frequency and wavelength via the speed of light using this expression shown here. And we've talked about some of the wave-like behaviors light can exhibit: reflection, refraction, diffraction, and constructive and destructive interference.